Okay, so it should be recording now.
Okay. I see the recording in the top left corner, so that looks good.
Yeah, now I'm just going to try to stream it.
Okay. Perfect. Yeah, I just see it streaming live on YouTube now.
Oh, perfect. Okay.
Oh, that was okay. So I guess we can get started. Daraj. Okay. Yep, just making sure you're still there.
Yep.
Okay. So hi everybody. Welcome to the to session 8B of STOC 2020. The theme of this session is, I'm going to call it nice results in complexity theory. We have a bit of a grab bag here of results. So just to remind everybody, the structure of the session, although I'm sure you're all familiar with it, each talk is going to be 10 minutes with roughly 5 minutes for a presentation and then questions afterwards. And then at the end of the session, we'll have an extra 20 minutes to clear up have some extra discussion or clear up any extra questions that people might have. Okay, so, and to all the speakers, remember that you should be timing yourself on your side for 5 minutes, and I'll be timing you as well. Okay?
Yeah.
And if everything's ready, our first speaker is Daraj Holden from MIT, who's going to be talking about non-signaling provers, or non-signaling proofs with a bounded number of provers in p-space. Okay, take it away.
Okay. I'll be presenting joint work with Yael Kalai on showing that non-signaling proofs with square root log n provers and negligible soundness are in p-space. Okay, so what do we mean by a non-signaling strategy for a multi-prover interactive proof? So what we mean is the provers are allowed to interact, but they cannot signal information about other queries. So what that means is that if you have k provers, for any subset of the provers, the distribution of answers only depends on the queries in that subset. So what is the motivation for studying non-signaling strategies? So the original motivation was to provide a clean mathematical generalization of quantum multi-prover interactive proofs. And later it was shown that there were applications to both delegation and hardness of approximation of computations. So what do we know? We know that for two provers, you can solve it in p-space, and poly-n provers can do everything in exp. So what we showed is we extended the result of two provers to square root log n provers. Again, remembering that this is with negligible soundness, and that we don't have results for other soundness regimes. And we still have a sort of question mark in the middle. So the main theorem is that a k-prover MIP with non-signaling soundness smaller than 2 to the minus poly k squared only exists for languages in space poly n and 2 to the k squared. And so this implies that a square root log n prover with negligible soundness only exists for languages in p-space. And the way we show this is that we go from a k-prover MIP with very small non-signaling soundness to a 2-prover MIP with non-signaling soundness that is bounded away from 1. And then we use this result that's known to show that it's in the right space. And so what we do is we consider this notion that we call sub-no signaling, which I'll explain. And we show that any game that has sub-no signaling value very close to 1 also has no signaling value that is bigger than 2 to the minus k squared. So what do we mean by sub-no signaling? So there's an alternate formulation of the non-signaling condition that there exists a family of distributions such that the probability that some subset of the provers outputs this answers is equal to this sim. And this is an alternative way of expressing that the provers can only depends on those queries. And sub-no signaling turns this into an inequality. So again, remember that we have this prover reduction that goes from non-signaling to sub-non-signaling, and combine this with what we call the heavy lifting theorem. And this completes the proof. And so to summarize, yeah, we have this k-prover MIP, and we turn it into a 2-prover MIP, and then use known results. Thanks.
Okay, thanks a lot. Are there any questions? Oh, I see one raised hand. Okay, Salil, you can go ahead.
Hi, can you say anything about where the k squared comes from?
It's from some technical parts of the proof. There are 2 places that this 2 to the k squared, well, there's one main place where this 2 to the k squared loss comes from, which is that there was an earlier paper about converting this notion called honest referee non-signaling to non-signaling. And that's where that comes from.
I see,
Okay.
thanks.
Okay,
Yeah,
should
we have
I
another.
answer these questions here?
Yeah. So Eric's raised his hand even, so I guess he can go ahead and talk. Go ahead, Eric. Or maybe I'm not sure if he can.
Okay,
hear.
I'll read
Yeah,
it out.
I can. Yeah.
So Eric asks, what is your conjecture about what happens between square root log n and polynomial? So to answer this, note that the result that shows that poly n can do all of x also shows that you can do time t with poly log t provers. So this sort of suggests an upper bound that more than polylog provers can't be in p-space, because that would imply something that we don't believe to be true. Personally, I think that the right answer is log n, just because it sounds nice and it seems sort of intuitively correct. Because we show that sub non-signaling is in p-space for up to log n. Okay, now Thomas's question.
Yeah. Maybe we can answer Thomas's question and then move on to the next speaker.
Okay. So Thomas's question is, does p-space hardness seem for you plausible as well? Actually, it was shown that p-space hardness has already been shown even for two-prover non-signaling games. And I didn't get to mention this due to time constraints, but okay, thanks.
Great. All right. Let's thank the speaker. And let's move on to the next talk, which is by Shuichi. So if we can get that set up. Maybe Diraj, you can stop sharing your screen. Okay, excellent. Okay, so great. So just to be clear, Shuichi, you're gonna time on your behalf too?
Okay.
Okay, and then, all right, so the second talk of the session is gonna be by Shuichi Hirahara, who's gonna speak about some unexpected hardness results for Kolmogorov complexity. Take it away.
So let me start with this motivation to study Kolmogorov complexity. In order to separate P from NP, Andrei Kolmogorov suggested that NP complete problems are probably too structured to be good candidate for separating P from NP. Instead, we should focus on NP intermediate less structured sets that somehow compress enough to separate, to prove separation. As a specific candidate, he suggested to consider resource-bounded Kolmogorov complexity. So let me quickly recap what is Kolmogorov complexity. Kolmogorov complexity of X is defined as the shortest length of program for X, program D for printing X. To make it formal, we fix a universal Turing mass U, and the T time-bound Kolmogorov complexity of X is denoted by K sub U superscript T of X. And it is defined as the shortest description for printing X in time T steps. We say that X is Kolmogorov random if you can't compress X into the length program of length X minus 1. And the set of random string is denoted by R sub K. For example, all zero string is not Kolmogorov random. And if you pick a uniform random string, it's going to be a random string with high probability. With this notation in mind, we can state Kolmogorov's approach towards P versus NP as follows. Let's take a polynomial time bound T, and let's try to prove the set of Kolmogorov random string can't be accepted in polynomial time. Then we can immediately show that P is different from NP because the set of Kolmogorov random string is in NP if it is polynomial time bound. But unfortunately, what we knew before is that if you take exponential bound, we can prove that the set of Kolmogorov random string can't be solved in polynomial time. And it has been an open question to prove the same thing for when the time bound is smaller than 2 to the n. What we are able to show in this work is to resolve this question for any super polynomial time bound. This is one of our results, but more broadly, we develop new proof techniques for analyzing Kolmogorov complexity in general. Let me mention another motivation to study Kolmogorov complexity. In fact, the reason why it is interesting to study Kolmogorov complexity is that it is closely related to pseudorandomness. More specifically, if we know that testing Kolmogorov randomness is easy, then we can show that we can break any hitting set generator. On the other hand, if there is no hitting set generator, it is also possible to prove that Kolmogorov randomness is easy. By using this relationship, there has been several hardness results for Kolmogorov random strings. Specifically, if you take any universal Turing machine, we can show that the P space is reducible to the set of random string. Similarly, next is reducible to the set of random string by using NP Turing reduction and so forth. Interestingly, there is an upper bound as well. If you take the intersection over all universal Turing machine, there is an EXP space upper bound on what you can reduce to Kolmogorov Kolmogorov random strings. Now, given this lower bound and upper bound, the natural question is what is the exact answer? It was conjectured by Arenda et al. That the upper bound should be improved to the lower bound. Namely, the lower bound of P space is exactly typed, and the P space should be characterized by the reduction to the set of random strings. In fact, there is a work by Goodholm and Burden which provides strong evidence for this conjecture. What we are able to show is that surprisingly, the conjecture is quite likely to be false. Namely, we were able to prove the lower bound from P space to EXP to the NP. And this refutes both of these conjectures. And what is interesting is that it bypasses the impossibility result of Goodholm and Burden. The key technical idea is that we consider a pseudorandom generator construction whose seed length is quite close to the output length. We constructed a EXP to the NP computable pseudorandom generator whose security can be proved by uniform reduction. And the construction is actually quite simple, which we call a k-wise direct product generator. So in this construction, you take a candidate Hall function f, and you take an error-corrected version of f tilde, and the direct product generator is just output. You take k independent input, z1 up to zk, and you evaluate it f tilde at this point. And the key property we exploit is that the advice complexity of the direct product generator is very small. It is roughly order log n bits. So to conclude, in this work, we presented several hardness results for Kolmogorov complexity and a surprisingly efficient reduction, which were previously conjectured to be impossible. Thank you.
Okay, thanks a lot, Shuichi. Is there any questions? Oh, Salil again. Go ahead, Salil.
Hi. Fascinating. Can you say anything about the ideas that go into the first result that you mentioned, or is it also related to what the second, the first result about the Kolmogorov, time-bounded Kolmogorov random strings for any super polynomial T?
Yeah, so it is a kind of related. Actually, first I found the proof by using the second result. I mean, I used direct product to prove that. Direct product generator to prove that the set of random string can't be solved in polynomial time. But after all, we were able to simplify the proof. So the proof strategy is to prove that there is a non-trivial SAT algorithm, satisfiability algorithm in some sense. And then we connect satisfiability algorithm to a lower bound question about the Kolmogorov random string. That's a kind of idea.
Great, thanks.
Cool. Is there any other questions? No, I have a question. So about the this is a very sort of naive, in some sense it's a very simple and sort of naive pseudorandom generator. Are there any connections with like so the pseudorandom generators that come up here that are related, that show you how to relate Kolmogorov complexity to these complexity classes? Are they in any way, like, is there a brief way to describe their relationship with this sort of more standard pseudorandom generators? Like this is kind of an exotic one. It's sort of, you don't normally consider pseudorandom generators with such a short seed length, for instance.
Yeah, so the key idea is that it is very, in the usual construction of pseudorandom generator, we would like to extend the seed as much as possible.
Yeah.
But the problem with that construction in this context is that the advice complexity grows up. Namely, in the reconstruction process of pseudorandom generator construction, you need to have a certain kind of non-uniform advice in order to do reconstruction. And the point is that if you consider this direct product generator, the advice complexity is very tiny. That's the idea.
I see. Cool. Thank you. So we have one more question from Ian Mertz. So the question is, where does so why exp to the NP?
Yeah.
Out of all other classes. Yeah.
That's a good question. So the point is that there is an advice which is ordered when. And in polynomial time, you can brute force that. But the problem is that we don't know which oracle is correct. But we know that there is at least one correct oracle. And in order to, it is in my previous work, we showed that if you, for exp to the NP complete problem, we can, if there is an oracle, one of which is guaranteed to be correct, we can compute exp to the NP. That's the key idea. And there is also matching, almost matching upper bound. So we need a different idea to improve that.
I see. Cool. All right. Thanks a lot. So I guess we're out of time. So let's thank Shuichi.
Thank you.
And then maybe we can move on to the next speaker. So Emmanuel.
Can you see my screen?
I can.
Okay.
Okay, great. So just a reminder to also record on your side. And our next speaker will be Emmanuel, who's going to be talking about smooth complexity of local max cut and other binary CSPs. So take it away.
Thank you, Robert. I am Emmanuel Vlatakis, and this is a joint work with Michalis Giannakakis and Shi-Chen from Columbia University, and Xinzi Chang and Chen-Hao Guo from Tsinghua University. And today, as you said, I will try to present some of our new results in smooth complexity of local max cut and binary constraint satisfaction problems. Let's start with our problem. In the max cut problem, given an undirected weighted graph, we want to partition the graph into two parts, such that the weight of the edge cut between those parts is maximized. Unfortunately, in its global optimum version, max cut is NP-hard problem. And even in the local optimum version, we know that the problem is PLS complete. And thus, a priori, we know that in the worst case analysis, there is an exponential execution path. However, in practice, there is a simple local search method, the flip algorithm, which runs almost linearly. So flip algorithm starts with an arbitrary configuration of the vertices in two parts. And as long as we can find some nodes that by flipping one of them, we can improve the weight of the cut, we choose one of them and we flip it until reaching a local optimum. So now the worst case analysis, because of the PLS completeness, is a very pessimistic way to analyze the flip algorithm. And thus the strongest result that we can hope is a smooth case analysis, similar with the seminal work of Spielman and Tenk for the famous simplex method. So in this model of analysis, we want to show that for every instance of local max cut, even the worst one, if we perturb it a little bit, then the flip algorithm would run quickly. Notice, first of all, that initially we can always rescale and normalize the weights to -1,1 without changing the combinatorial difficulty of the problem. Then we can add some small variance noise and compute the worst expected running time. Now, to avoid the discussion about the kind of the noise that we will use in our analysis, we follow a generalized perturbation model. We sample the weight of the edges of the input graph from a distribution with bounded density by a parameter phi. Now, if phi is close to infinity, you can see that we allow very concentrated distributions close to the worst case analysis. And if phi is close to 1/2, our analysis corresponds actually to the average case analysis with a uniform distribution. For special kind of graphs, like the sparse ones or fully complete graphs, we know that flip algorithm runs in smooth polynomial time. Now, for the arbitrary case of an arbitrary graph, the best previous result was n2 log n by Edsheil and Rogling. Unfortunately, in the first part of our work, we saw that all these previous techniques has been proven tight with giving some examples of graphs that cannot give better result using those techniques, but we achieved to present a new analysis framework which improves the smooth running time complexity to n square root of log n time using some new ideas. Additionally, we show that our analysis is not limited only to the max cut, which actually corresponds to an Ising model with XOR constraints, but to a general family of binary constraint satisfaction problems, improving with that way the smooth complexity of many other famous problems like local max to SAT, affiliation games with best response dynamics, or Hopfield neural nets. Now, to give a very sketchy sketch of our idea, the real question is how much unlucky can we be? Now, the max cut after normalization, it is n squared. So the real question is, can be all the flips epsilon small in their improvements? If that horrible event happens repeatedly, then the algorithm may run very slowly. Now, if the flips or the combination of the flips were independent, then this event has exponentially small probability, and we could somehow safely exclude it. However, in an arbitrary graph, flips are too correlated because of the underlying graph structure. So here are our major ideas. We show, first of all, that we can either shrink the size of the blocks that we need to analyze by deleting some irrelevant flips from the analysis, but with a careful way, without violating the correctness of the analysis. Or if we cannot delete, then we show that this is never against us, and we can increase always the number of independent flips or the number of independent combination of flips. Thus, always we can increase the density of independent components in this procedure inside the block that we will analyze, and we can increase it to 1 to square root of log n, giving the algorithm n to square root of log n. Now, the real open question is if someone can achieve the ratio to be close to 1, then all the bad events would have a really exponentially small probability, and we can show a smooth polynomial time. This is our conjecture, even for the arbitrary case graph. Now, besides this open question, I would like to close with some other open problems. First of all, typically, we start with probabilistic or average case analysis, which is easier as a model than smooth analysis. But right now, we don't have something better for these relaxed models of complexity. And this is a little bit bizarre. So is there a simpler solution, a much more simpler argument for this kind of analysis? What about more complicated problems with multiple variables like local max 3 SAT or max k SAT? We don't have anything yet established for this unexplored area. We're looking at it right now. And finally, it would be interesting to see if someone can apply this increasing density technique by deleting irrelevant to the analysis flips in local search methods to other problems of smooth analysis. Thank you very much, and please don't hesitate to ask any question.
Great. Thank you very much. Are there any questions? Oh, I see a question here. So a question from Jafarov. Is there any structural reason for getting square root order, like the square root order log n?
Yeah, this is a very good question. So the problem is actually that, what is the idea? That you would like to keep only the independent events in order to create the exponentially small probability. So if you have some really independent events, you would like to show that all the other events are irrelevant from your analysis. Now, if you can delete all the others, but don't violate the correctness of the rest of the flips or the combination of the flips that you have kept, then you would have the smooth polynomial time. The issue is that you cannot do that because there are lots of interconnections between the flips. So in order not to violate the correctness of the analysis, the best that we can do is to delete some nodes, and the best that we have achieved until now to delete is to go from a ratio to 1 over log n to 1 over square root of log n. So to wrap up, the issue is the interconnection between the other flips that you want to delete and keep just the independent ones.
See. Okay. We have a question from Madhur, who's asking if the original graph is unweighted, do you apply the noise in this? This is a question about the smooth complexity model. Do you apply the noise to all the pairs or only the ones that where edges are already there?
If the graph is unweighted, the problem is easy because if the problem in that case the max cut is n squared and you have at least one step. You have by integer 1 for each step, so you know that.
Right, it's going to terminate within.
Yeah, you can solve it in n squared totally. Now, maybe it is an interesting question to see if you can solve it even better with some perturbation, but we know that it is smooth polynomial. We know that it is actually deterministically polynomial.
Okay, great, thanks. And then there's a question from Sloan Nitert, who's basically saying the flip algorithm is a little bit underspecified in your talk. What's the exact rules that are used in the flip algorithm?
Very nice question. Actually, we saw that for any criterion, this is a family, this is a correct question, because whenever I can flip some, the idea is that I collect the nodes that can improve locally my max cut, but the question is how I choose between them. So for any criterion, our analysis can be applied. So this is correct that it is underspecified because it is a large family, but we answered this question for the whole family of different criterion of flipping.
Okay. So so it looks like so a follow-up question to that was whether or not you think you could do better if you made particular choice on the rule. So if it's more specific.
This is a very interesting question. There are many interesting questions, like if you can specify the criterion, if you can have better results. There are also questions, something like for the complete graph, can we improve the polynomial exponent that we have using our technique of deleting irrelevant flips? All these ideas are really open and we are working on them right now.
Cool. And then finally, there's an answer to Madhur's question. He's applying noise to the existing edges of the graph, which is apparently called the arbitrary graph model. Okay, great. All right, then we're up for time on the session, so let's thank the speaker.
Thank you very much.
And let's move on to the next. So. Okay. That's great. Okay, so just a reminder for at least one of you to time on your side as well. And the next talk will be given by both Cristobal and Michael Yampolsky about how to lose at Monte Carlo. Okay, take it away.
Okay, thanks, Robert. I'm going to start. So the Monte Carlo method was developed by Stanislav Ulam and John von Neumann in 1946 on their work on nuclear bombs at Los Alamos. And it has since become ubiquitous in simulation, numerical simulation of nonlinear dynamics. And it was impossible in 1946 that those computers to simulate nuclear explosion, but it's still impossible. It's too complex. If you want a more familiar example, then you could look at weather prediction, which is also an example of a complex system, which is impossible to deterministically do on a computer. So the technique, the Monte Carlo technique, is should be fairly familiar. You pick a large number of initial values, you run your computer simulation for each one of those values, then you take an average of the results and you hope that this averaging gives you a meaningful statistical description of the outcomes of the actual event that you're simulating. So that's why your weather forecast could give you a 40% chance of rain. That's a result of Monte Carlo simulation. And if you want to be a bit more precise, then you would do something like this. you consider a discrete time dynamical system, which is given by some map in F from a finite domain in a Ren to itself. You pick k initial points in D that are randomly chosen. And then for each one of those, you run your map for n steps, and then you average. You average over the orbits of F, and you average over the k points, and you get some sort of a probability measure, mu km. And the postulate then, the empirical belief, is that when kmn are large, when they go to infinity, these probabilities converge to a limited statistical distribution. And that distribution describes the long-term statistical behavior of your system.
Right. So we want to study the cases in which the system has a possibility for this method to work, and so we consider what's called physical measures. So a measure is physical if there is a positive Lebesgue measure set of initial conditions, such that if we start at any of these points and look at this Birkhoff averages, this finite measure converge to this physical measure. So it's physical in the sense that we should observe it with positive probability. And it's known that in general, a system doesn't have to have a physical measure, or it can have infinitely many of them. But we will be interested in the cases, in the nice case, in which the system has a unique physical measure. And what we want to see if whether this physical measure can be computed. So a measure is computable in our sense, or in the sense that we want, if there is a machine that can compute intervals of simple computable functions with respect to this measure at any prescribed accuracy. So for example, in the unit interval, a measure is computable if there is a Turing machine that on input an interval with rational endpoints PQ and an integer n gives a rational number which is exponentially close to the actual value of the measure for that rational interval. And the machine has to work for all rational intervals and precisions. So for example, from this definition, we immediately see that Lebesgue measure is a computable measure, and any measure with a computable density will also be a computable measure. So the examples that we will look at are the logistic family. So these are the simplest nonlinear system that you can conceive, and it's famous because it's simple, but it shows extremely complex behavior. So here, this is the bifurcation diagram of this system. So here we have the parameter, so A, and this here is the set of points towards almost any initial condition will converge. So we see if we increase the parameter, the complexity of the attractor grows until we get to a region where it's very complicated, including this last part where the system is fully chaotic. So that last value is 4, and this particular map actually, incidentally, is known as Schuland von Neumann map. So they use it as pseudo-random generators for their study. And it's an example of a fully chaotic system. And if we run a Monte Carlo simulation for this map, we see that these finite measures very quickly approach the unique physical measure of this system, which is therefore a computable measure.
Right, so our main result is the following theorem. So in the logistic family, there exists an uncountable set of parameter values A, for which the following two properties hold. So first of all, there exists a unique physical measure mu, which depends on A, and such that its basin has full Lebesgue measure. So for almost every point, the Birkhoff averages converge to mu. And the second property is that mu is not computable relative to A.
Right. So in particular, the Monte Carlo approach, and actually any other algorithm, will fail if we use it to compute this measure. And it's not because there are no such physical measure or too many of them, but simply because the nice right measure that we would like to compute can just not be algorithmically approximated. So that's the end of the talk. Thank you.
Thank you.
Great, thank you. Are there any questions?
I have one question.
Yeah, go ahead.
So the logic map is something like a very famous map that it is connected with New York house. So I would like to ask if you have some similar results or some intuition about one-dimensional maps that they have chaotic phenomena and they are connected with this intractability kind of results.
Well, this phenomenon, so this family is in a certain sense is universal, meaning that for any shall we say complex family of one-dimensional dynamical systems, the dynamics of this family will be a subset. So you're going to observe the same phenomenon in any non-trivial family of one-dimensional examples.
See. Okay, are there any other questions? I guess I have a question. So can you say anything more about so the only thing from the statement of your theorem about these set of like bad A's, which have this bad behavior, is that it's uncountable. Can you say anything more structurally about it other than just uncountability? Like, is it measurable or is it anything like that?
We know that it has measure 0 in that family.
Okay. I would have guessed.
Yes, but in higher dimensions, for example, for polynomials in dimension 2, we believe that it could be bigger. We don't know how big, or probably generic. And yeah, that's probably that. And if we ask the same question about complexity, well, then there will be more bad parameters, and perhaps even positive probability in higher dimension.
Cool. Okay. Well, if there's no other questions, let's thank the speakers again. And let's thank all the speakers from this session. Now there's usually a 20-minute break. If anybody has any questions for any of the speakers, they can feel free to go ahead. Oh, here's a question. Here's a question for this most recent talk, actually. Are there any rational or algebraic A which are contained in the set of values where f of A's measure is not computable?
We actually don't know. It's not right. So there is no somehow the parameterization of such families is not really natural in any sense other than algebraic. So it's hard to relate the things like algebraic properties of the parameter values with the actual statistical properties of the map. And this is not, since it's not an parameterization invariant question in any sense.
Oh, I see. Right. Okay. Are there any questions either for this speaker or maybe for any of the other speakers from the session? Oh, you have another one? Oh, are the A's for which this theorem is true at least computable?
We believe, we don't know for sure, but we believe that we can compute some parameters.
Yeah, we think so. It becomes a bit cumbersome, but we think that's, let's say we conjecture that we can produce a computable
example. Yeah.
So the result that so I guess in the process of proving this, it must be sort of highly non-constructive, whatever your proof technique is.
So
that's right. Yeah.
Right.
I wouldn't necessarily say highly, but
yeah. Well, yeah, it's open if it's computable, so probably not highly.
Right. It's non-constructive, but can probably some work can be made constructive for some philosophy.
Cool. Okay, great. Yeah, if anyone else has any other questions for any of the speakers, anything like that, feel free to go ahead. Okay. I actually have another question for Diraj from the first talk. Diraj, if you're still listening.
Yeah.
Yeah. So you mentioned no signal. So your entire talk is about no signaling proofs ultimately.
That's right.
So you mentioned that the no signaling proofs generalize provers that share some entanglement. So how does this compare to this like MIP star, these sort of other models with entangled provers?
So, well, basically, any quantum strategy is non-signaling, but there are a lot more non-signaling strategies than strategies where you can just share entanglement.
I see. I see. Right. So, and that difference is, I guess, why you get a p-space upper bound as opposed to
Yeah. Well,
Yeah, right.
X upper bounded general.
or X upper bound. Yeah, right. Okay, thanks. Yeah. Okay. Well, if there's no other questions for any of the speakers or anything, I'd like to thank all the speakers again for lovely talks and remind everybody that the full versions of the talks are on YouTube. Oh, we have another question for Diraj here. Are there any strategies that yield different computational power between quantum and non-signaling?
Yes. In fact, the CH-SH game, well known for showing a separation between classical and quantum, also separates quantum from non-signaling. You can show fairly easily that the CH-SH game has non-signaling value 1.
Okay, great, thanks. Yeah, okay. Well, I guess I'm not sure if the technical lead is there. It seems that the questions are pretty much no other questions. I guess we can, if not, we can end the session.
All right.
Okay.
Sure, I'll just end the recording and then I'll end the meeting.
Great, thanks a lot. All right, well,
Okay.
thanks
Thank you.
everybody for attending, and thanks for the lovely
Thank
talks.
you.
Bye.